All right, let's look at part two of the fundamental theorem of calculus. The part two of the fundamental theorem is very important in a practical manner because it says that we can evaluate definite integrals by using antiderivatives. Part one is important in sort of a theoretical way, but part two gets used all the time for solving problems. So let's look at it. It says that if f is continuous on the interval from a to b, then this indefinite integral here can be evaluated by doing big F of b minus big F of a, where big F is any antiderivative of little f. And I want to talk about some notation and some stuff before we do any examples. But first off, notice when we're doing this subtraction over here, it's F of the top minus F of the bottom. That's a sort of a common mistake I see people make, but it's F of the top minus F of the bottom. And two different notations that we can use for this are shown here. To denote this F of B minus F of A, we use this vertical bar, or sometimes instead of just using a bar on one end, especially if you've got other stuff that's added on out here, we can use these big brackets with the A and the B on the outside. So I've actually got a bunch of examples here that I want to do. So we'll cut this up into probably 2 or 3 videos. But let's go ahead and do a few of these just to see the notation, see how all this works. So evaluate from 0 to 3 of 9 minus x squared. All right, so what I'm going to do is take the antiderivative of this. Antiderivative of 9 is 9x. Antiderivative of x squared is 1/3 x cubed. And we're going from 0 to 3. So if I plug my numbers in, I'm going to do 9 times 3 minus 1/3 times 3 cubed minus 9 times 0 minus 1/3 times 0 cubed. All right. So this one over here is going to be 9 times 3 is 27 minus 27 over 3 is 9. And over here, this is all 0. So I wind up with 18 for my answer. And that's really all there is to it. And it's kind of interesting that this gives us exact values. What I'd like to do is check this by comparing it to the calculator. So let's do this. I'm going to have to pull this up. Let's see. Area under a curve. All right, if I put in 9 minus x squared, and if I go from 0 to 3, and right now I'm using 10 rectangles. I don't really have this on the screen very well. But using 10 rectangles, it gives me 19.3. If I up my number of rectangles, you can see that it is getting closer and closer to 18. So that corroborates it. All right, let's do some more examples. Okay, this is an interesting one here. You know, the other day we did an example, or we saw that this was 2 the other day by just looking at the calculator we just played with and saw that this gave us 2. But now we can use the fundamental theorem and see that it's exactly 2. So let's see. If you integrate sine, you get negative cosine from 0 to pi. Now I'm going to plug this in. I get minus cosine of pi minus cosine of 0. right, let's think about cosine for a second. Cosine looks like this. All right, cosine of pi is -1. And cosine of 0 is 1. So we've got lots of negatives going on here, but this winds up being, let's see, inside of here, that's 1. And plus 1 gives us 2. So sure enough, if you draw a sine, this area inside of here is exactly 2. All right, let's do this next one. 1 plus 3x. This is one that we could do using geometry because, if you think about it, 1 plus 3x, that's from 0 to 4. That's going to be this trapezoid in here. But let's do it with the fundamental theorem. If you integrate 1, you get x. If you integrate 3x, you get 3/2 x squared. Again, from 0 to 4. So plug in the 4, you get 4 plus 3/2 of 16. Plug in the 0, you get 0 plus 3/2 of 0. So this whole thing's 0. This is 4 plus 16 over 2 is 8 times 3 is 24. So that'd be 28. Should we check that one on the calculator? Yeah, why not? Let's do it. Let's see, what was it? It was 1 plus 3x. So it gives us that. Yeah, it's taken a while to update because of all these, because I'm using a crazy number of triangles, or rectangles. Out. So we've got that. This has given us an area of 16.36, but I don't have my endpoints right. My endpoints need to be 0 to 4. And let's see, 27.76. If I start adding more rectangles on, actually if I do that and if I change this to midpoint, it should be dead on. Yeah, 28. Why is it dead on? Because if you zoom in, because this is a straight line, the error that's where it's overcounting and the error where it's undercounting exactly cancel each other out. But anyway, that gives us the same thing that we got on the using the fundamental theorem. All right, we've got a few more examples. I'll put those in the last video.